Okay, we're finally getting down to the weather in where we live, the mid-latitudes. So we're going to talk about some things with that. And we're putting everything you've actually learned kind of in that area. So what systems actually shape our weather? Well, first let's talk about air masses. We've talked about them before, but they form from a high pressure where the winds hardly move and allows the air to take on the characteristics of the ground. So look at Canada, for example. A lot of that ground in the wintertime is snow-covered, pretty dry. So it's going to take on the characteristics of a cold, dry ground. That's a continental polar air mass. Arctic air masses, of course, come from even higher up, but they're even drier and more snow under them, so they're even colder, less sunshine. You notice that maritime air masses form over the oceans. There are maritime polar ones that form over the North Atlantic. And they're going to be a little bit wetter, but they're still going to be cool. Not as cold as continental polar because they don't have ice under them. And then you have the tropical ones. If you look in the desert southwest of the U.S., you're going to get the continental tropical, which is just a dry, hot air mass. A lot of times in summer you see that. And then you have the maritime tropical air masses, which are very moist and very tropical in the sense of fairly warm and very, very humid. So as these air masses leave where they are, for example, if you have a Canadian air mass coming in the United States, and say it hasn't snowed in the United States, well, what happens is the ground underneath it is absorbing a lot more solar energy. It's going to get hotter. That's going to cause mixing to occur because it's heating the lowest part of the atmosphere and creating instability and convection. So you wind up transitioning that air mass over time. The further it travels without snow, the warmer it's going to get. The longer it travels away from its source region, the more time it's away, it's going to just become less and less. Tropical air masses, on the other hand, they do change. They may become drier with time, but the bottom is going to cool, but that stabilizes it. So what happens is you wind up with a tropical air mass kind of hanging together a little longer. It lasts a little further into the system. This is just a three-dimensional picture. We've talked about the atmosphere being three-dimensional of a stationary front. There's no warm air advancing. There's no cold air advancing. Remember, warm air is always lighter than cold air, so the warm air is always going to rise up and over a cold dome of air. So that means you're going to have clouds further and further over top of that cold dome that are going to be like cirrus clouds and then gradually lower the closer to the warm front you actually get, or in this case, a stationary front. The precipitation is going to extend into the cold air. Probably not much into the warm air in this situation. This is a warm front. The warm front's advancing. All a warm front is warm air replacing cold air. So if a warm front passes your house, the temperature is probably going to go up. If a cold front passes your house, temperature is going to go down. And here's a cold front. Remember, cold air is very dense, so the warm air tends to go up pretty quickly in front of it, so you wind up more with convection, more thunderstorms along a cold front. And you can see cold fronts typically come from the west, but sometimes they come out of the northeast. I get these in the spring sometimes, and even in the fall, the backdoor fronts coming down the Appalachians, and they ruin my days because notice they're coming along the east from over the ocean, so they'll pick up moisture from the ocean, bringing into my house. It winds up being a cloudy, cool day. Typically, occluded fronts form late in the cyclone's life cycle, and there are two types of occlusions. There's a cold occlusion and a warm occlusion. Think about a cold occlusion. The cold air, the coldest air is actually advancing, and the cool air is kind of retreating, but all the warm air is pushed aloft. That's an occluded front. If you have a warm type occlusion, there is cool air that has pushed the warm air aloft, but the coldest air is actually retreating as well. So the coldest air is being replaced by cool air. This is the Norwegian cyclone model. It works. What happens initially is you have a trough of low pressure aloft. And there's divergence, which causes low pressure to form at the intersection of a warm and a cold front. One of the things lows like is strong temperature contrast. When there's strong temperature contrast, you're going to get a stronger jet stream. So the stronger the temperature contrast becomes, the stronger the jet stream gets, and the more divergence is available to these lows. So you can see with time, the jet stream drops a little further south, bringing up more heat and humidity and dropping in colder air. And the low begins to intensify. Finally, maybe the upper low itself actually forms right over top of the cold surface low. And remember, in a cold air, pressure drops much faster in the vertical than it does in warm air, so that you wind up with a low right over top of where this is. So here you can see this very strong divergence aloft, and the development, it develops a comma head with time. And eventually the occlusion begins. And when that happens, you get a dry slot to the southwest of it as well. And the more the occlusion is, the more the dry air kind of comes in that area. And you'll notice there's a triple point where the occlusion, warm front, and cold front all meet. Very interestingly, that is an area favorable for new cyclone development. So eventually you may get this strong low weakening and the new low forming right here, which takes over and becomes the stronger of the two. And here is just the conveyor belt model. The conveyor belt model is talking about air mass motion. Think about it. You have a warm air mass coming up on the warm conveyor belt out of the tropics into the low. So it's pulling it into the low right here off of North Carolina. Lots of warm, moist air. You have a cold conveyor belt, a little bit under that actually, that's coming in off the Atlantic, being pulled down on the back side of it. And then you have the dry air stream, the jet stream coming in underneath it. So moisture is coming from the cold conveyor belt and from the warm conveyor belt. So, and again, just looking at a cyclone and understanding a little bit of the precipitation that goes with it. When the cyclone is moving towards you, there's dropping pressure. One of the great ways to track a cyclone is finding where the pressure is falling fastest. The motion of the cyclone is probably in that direction. Where the air pressure is rising faster, that's where the high pressure is coming in behind it. And you can see the precipitation around the cyclone. In the wintertime, to the northwest of the cyclone will tend to be snow, maybe even snow showers. Along the cold front, there'll be thunderstorms and rain showers, and a more steady, drizzly rain, miserable conditions to the northeast of the low. Sometimes that can even be snow if it's cold enough, or ice. And here you can see the different tracks of lows across the United States and where the cyclones typically form. A lot of cyclones form in Colorado that affect Ohio, for example, and if you're on the East Coast, some of them form in Texas, or some of them form in the Gulf of Mexico, and some of them even form right along North Carolina and move northeast, causing tremendous nor'easters. Again, here's just looking at a track of a low, and you can see the snow out on the left side of it, and more rain on the right, some icing maybe near the snow, showers and thunderstorms. But say you misplaced that low just a little bit, maybe only 20 or 30 miles, but it could have a big impact on what your weather is. And here again is this cold core. As the low deepens, the thicknesses drop because it's cold all the way up. That's a cold core cyclone. That's a regular low that you're seeing every day, but it's also called an extratropical cyclone. Before they occlude, many times this air is to the west of the low or northwest of the low, has a tilt to it. Warm core cyclones, and there are warm core thermal lows. Particularly, we'll look at one here in a little bit on a map, but it's over this, typically where it's very dry, very hot, arid lands. What happens is, again, here is a case where it's warm, the temperatures cause the pressure to drop much slower in the vertical, so what you actually wind up in the vertical is an anticyclone or a ridge aloft. So, and again, cold core anticyclones come down with polar Arctic highs or behind a strong cold front. Sometimes an example would be a Siberian high. They're very stable, and they tend to be very clear, which means when you have good radiation of cooling over snow-covered land, you wind up with an even colder air mass. Warm core cyclones tend to form well south of that Arctic air, and they can change with time as they get modified. There are such things as lake and sea breezes. Lake Erie is a classic example. Sea breezes along the east coast of the United States or Florida, particularly in the springtime when the temperature contrast between the lake or the ocean is greatest with the land, which happens a lot in the spring. You wind up with stronger sea breezes. Valley breezes form and mountain breezes and circulations into valleys, all based again on how solar radiation is absorbed in these areas. Interestingly, out west you can have Chinook winds. Sometimes they come from the west down into the plains and they're warm. There have been instances in parts of Montana, Wyoming, where the temperatures have risen in a matter of a couple hours when a Chinook wind hit of over 70 degrees, where they've gone from like 20 below to 50 above. That is the process of air descending, being pushed down, warming because it's descending, and being compressed. Santa Ana winds out west. If you ever want to know why it is so daggone hot in the desert out here, look at all the mountain ranges it's got to go across to get to that area. And the air is coming from the west or even from the east sometimes into Death Valley, and it's dropping down very low because it's actually below sea level. Hababs are just dust storms. We get some in the southwestern U.S., maybe even into western Texas sometimes. A lot of times they can form when a strong downburst exits a thunderstorm, a strong downdraft, and it pushes the dust into the air and causes literally like a mud almost as it's moving along. Heat bursts are convective rain showers that never make it to the ground. I experienced one in Oklahoma City one time in the evening where it was very dry out, but a thunderstorm developed over top of us. The rain never made it to the ground, but the air was pushed down, and as the air temperature warmed from compressional heating, it literally rose from the 80s to over 100 degrees in a matter of about a half hour. So it's a unique event. I just wanted to show you quickly here. Let's just start with where things are right now. There's a low east of Hudson Bay, 1,008 millibars, and there's a low right here over Southern California. That's the heat low. The way you can see this is look at the temperatures. They're extremely hot out there. It's already early in the morning. Here you have a very strong cold warm front here with colder air above it, and the cold front coming in here. So you have temperature contrast. You don't have that temperature contrast around the heat low. And if you were to look at the upper air at this time, you can see here's the cold core system that goes with this low over Hudson Bay, and a jet right rear right in here where that low is, with causing divergence there for that low to take shape. Out here you actually have high pressure. You can actually see it rotating around. So it actually has formed an anticyclone. So everything you've just been told actually is working. And here you can look at it on satellite, and you can actually see a little bit of a calm ahead here. Not a whole lot, but it's the best I got right now. There is a better one out in the ocean, right in here, more occluded. So let me know if you have any questions about this.